used actually in some applications like denoising, especially when it comes to images. And today we'll talk about it in both cases when it comes, let's say, to one-dimensional signals and two-dimensional signals. All right, so specialized filters. So the outline will talk about some optimal linear filters, non-linear filters, and now it's going to be our main topic, a median filter. So we've seen high pass, low pass, band pass, and band stop. So all of them, they correspond to the frequency classification. So high pass, for example, passes high frequencies, low pass, low frequencies, band pass, a certain range, and band stop is kind of the complementary for band pass. So it's basically rejecting this range of frequency. Now, this median filter cannot be represented, let's say, in Fourier or frequency domain characteristics. In fact, the main task for the median filter is to remove outliers. Many systems actually, sometimes due to disturbances in the surrounding environment, there are some spikes. So for example, assume that there is a discrete signal like this, and then you have this one here, and you continue having this kind of samples. So someone might assume that, okay, there's an issue with this one. This does not look normal. This is what we call actually an outlier. An outlier is just a sample that has a large value or has a different nature and value when compared to other samples in the signal. All right, so we'll talk about nonlinear filters. We'll give the focus for this one. So they do not apply the frequency response concept. We cannot do this Fourier analysis, band pass, band stop. It means that are characterized by linear difference equation. Also, the median filter has no impulse response. We don't have such H of N. There is no Fourier transform used to calculate the frequency response. So those are main characteristics of linear filters. They don't have this difference equation, and there is no Fourier transform for this thing. An example or typical example of nonlinear filters is the median filter. So it is a type of nonlinear filter that preserves discontinuities. So for example, image edges or spikes, etc. Okay, we'll talk about the images later. If we have time in class, we might give an example on an application of median filter in images. All right, so the median filter, it replaces each pixel with the median of all the gray levels or like values. Because the gray levels are more into images. So in local neighborhood, generally defined by a square window. So that's an image kind of dimension, not one-dimensional signal. We'll give actually two examples, one in one-dimensional and one with two-dimensional. So for example, you have this value of samples here, you have small values, then you have a sudden change. This is what you usually call a spike. So you have small values and then you suddenly have large values. So that's a large discontinuity. There are two ways to treat or deal with this spike by using averaging filtering. So you take like a certain neighborhood, take the average, then another neighborhood, average, and so on. So you keep sliding this window. Notice here that there is no actual filter. So you slide a window and within the scope of this window, you look at the samples, you take their average, and that's the job of the average filter. Another one is dealing with median filter, and the median process is simple. You just sort the values, and then you take the point at the middle. So let's assume that you have these samples, 1, 10, 3, 5, and 6. And I ask you, like, apply a median filter process with a length of 3. So what you do here, you pick these 3 samples. So that's what we mean by the length of the filter is 3. So you have these 3 samples and you sort them. So you have 1, 3, and 10, and then you take the point in the middle. So the median of those is just 3. Then the second window will be those 3 samples. 3, 5, 10. You take the one in the middle. So that is a 5. Then you take these 3 samples. Sort 3, 5, 6. You take the median, it is 5. Median is 5. Now notice an issue here that the length of the signal at the beginning was 5. The output became 3. So to solve this issue, there is a pre-processing we do to the input signal, which we call zero padding. So zero padding, basically I'll go to the edges of the signal. I think we've done that in signals, the zero padding or no? Yeah, in signals, the system does not do that. So zero padding, the edges of the signal, I add zeros here and 0 there. So when you apply the filtering, the output will have the same length, 5. Now we'll see an example and see how the process works there. All right, so one of the advantages of median filters is to remove the impulsive noise. Sometimes when you have a lot of low value signals, when you apply a median filter, it may, let's say, discard all values here, say for example like this. So you have these values. When you do the sorting, the 0 will become in between, so you'll get a 0 here. You will get a small sample here. It depends actually on the size of the filter. So this one here does not specify the size of the filter. Averaging filter is also a solution. Averaging filter, basically you do not take the median, you do not do sorting, you just take the average of the samples. Our focus will be in the median filter, but there are other types of nonlinear filters. Averaging filter is one of them. All right, so what you'll be questioned during the exam is apply a length 3 median filter to the following signals and draw both the input signal x of n and output signal y of n. So my input signal length is 2, 4, 6, 1, 2, 3, 4, 5. So we have 7 samples. 7 samples. So the output also must have a length of 7. Now the first pre-processing is to do zero padding. Now with zero padding, I will have another sample here 0 and another sample 0. Now let's do the median filtering. So median filtering, I will take length 3. So I'll take this 3 samples here, sort in ascending order. So I have 0, 2, 4. What is the value in between? Like at the center is 2. So the first sample is 2. Now, the other window, 2, 4, 6. So 2, 4, 6. So the second sample will be 4. Then I have 4, 6, and 1. So it's going to be 1, 4, 6. So the output will be 4, taking the 1 in half. So that's 4, 6, 1. Then I have 6, 1, 13. This one, 4, 6, 1, right? So sort them in ascending order. 1, 4, 6. You have to do sorting. You have to sort. Then we have 6, 1, 13. So 6, 1, 13. We do the sorting 1, 6, 13. So I'm going to get 6. Then I have 1, 13, 2. Sort 1, 2, 13. I will get 2. No question? So it depends on the value. So initially I have 2, 4, 6. When you do sorting, you'll get 4. Now I have 4, 6, 1. Sorted 1, 4, 6. So it's going to be 4. Now see the thing, the 0 is there, right? So the length is 3. So 0, 2, 4. When you do the sorting 0, 2, 4, you will get 2. That's the first sample. Then when you have the length 3, 2, 4, 6. So 0 is done. Like it's like sliding window. Yeah, 2, 4, 6. That's the first one. Then the second one, 4, 6, 1. When you do the sort, 1, 4, 6. That's the second one. All right, so we have 1, 13, 2. So it's going to be 1, 2, 13. So the value is 2. Then we have 13, 2, 5. Let's sort. So we have 2, 5, 13. So the center will be 5. Then the last 2, 5, 0. When you do the sorting 0 to 5, the answer will be 2. So to confirm, just count your samples. 1, 2, 3, 4, 5, 6, 7. All right. Okay, now the question is draw both x of n and y of n. So let's draw x of n. Let me use the eraser to remove those. Okay. So let's draw the input first. For the first sample, that's 0, 1, 2, 3, 4, 5, 6. Those just indices. So at 0, I have 2. At 1, I have 4. At 2, I have 6. Something like this. I have 1. Then I have 13. 13, I think, will go beyond like this. Then 2, 5, something in between there. So that's my input signal. Now, if you want to like make a quick conclusion, like you know that this like an outlier doesn't look normal compared to the other values in the signal. Now the output of the median filter, let's do the same. So 0, 1, 2, 3, 4, 5, and 6. So I have 2, 4, 4, 6, 2, 5, and 2. This one kind of looks, smoother when compared to the original signal. There are no outliers, and that's the typical application for median filters and signals in general. Clear? All right. So that's for one-dimensional signals, straightforward. Now, what about two-dimensional signals, or usually images? An image actually is just a matrix of numbers ranging from 0 to 255. The 0 is going to be the dark pixel. I'm talking about grayscale images. So the 0 is a dark pixel, black, and the 255, that's a bright pixel, white. And any value between 0 to 255 is going to be a gray level, a grayscale. The larger the value, the brighter it is. The smaller the value, the darker the pixel is. The higher the value, the brighter it is. Yeah. Now, this is a small example here, 3 by 3 matrix, and I asked you to apply a 3 by 3 median filter for this matrix. Again, what is the first step? Zero padding. So how to do the zero padding? Everywhere, at the edges. I'll add 0 here, 0 here, 0 here, 0, 0 at the corner, 0, 0, 0. And a 0 there. Okay. Then start by a window 3 by 3 and do the sliding. So the output must be a 3 by 3 matrix. So let's see this value. This value is the result of applying the median filter in this window, the 3 by 3 window. Now, when you do the sorting, it's quite easy to see that the median value will be 0 because I have 5 zeros and 4 other values. So when you do the sorting, you have 5 zeros, then 4 other values. The central point will be 0. Or you want to do the sorting manually. So it's going to be 0, 0, 0, 0, 0, 1, 2, 4, 9. 1, 2, 4, 9. And you pick the point in the middle. That's the median. So that's going to be 0. And you notice it's going to be the same for all other corners. For this corner, that's 5 zeros. So that's a 0 there. Similarly, for this corner, okay, so you have 5 zeros. That's a 0 there. And there is a 0 here. Okay. Now let's find the value in this pixel here, which is basically the overlap, or sorry, this window here of values. Now notice here I have fewer number of zeros. So I have 3 zeros, 0, 0, 0. Then I have these values. So I have 2 ones, 1, 1, 2, 3, 4, 9. 2, 3, 4, 9. Make sure the length is 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9. When you do the sorting, the value in between will be 1. So the value is 1 here. Clear? Again, so I'm taking like the upper half of this square. Similarly, if I want to take this half to find the value of this pixel. So I will have 0, 0, 0, and then 1, 2, 2, 1, 2, 2, 3, 4, 9. And the point in between is 2. Now this one here, find the value of this pixel. I'll have 3 zeros. Then 2, 2, 4, 2, 2, 3, 3, 4, 4, 9. Okay, so it's going to be 2. Now the value at this pixel is going to be this part. I'll have 3 zeros again. Then I have 1, 3 twos. 1, 2, 2, 2, 1, 2, 2, 2, 4, 9. So that's going to be 2. Now the last one here, the center is basically this full thing, right? All right, so let's see the sorting. I have 1 and 1, then 2, 3 twos, 2, 2, 2, 1, 3, 4, 4, 9. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So the pixel in center will be 2. Now, if you want to do a quick comparison, you notice like when it comes to these values, the number 9 looks like an outlier. Now here I'm getting values 1, 0, 0, 2, 2, whatever. All right, so let's do this in MATLAB because that's it. That's the lecture. So let's do it in MATLAB. Yeah, MATLAB always does this. It takes time to load. No, that's it. The tutorial was just the two examples we did solve. I'll open MATLAB online, is faster. Okay, whoever wins. Okay. Okay, we'll do the MATLAB online. Okay, so let's try both examples. This one here. So I have x equals, okay, the browser, x equal 2, 4, 6, 1, 13, 2, and 5. Okay, so y equal median x, and the size of filter is 3. Okay, I haven't done median filtering for a while, so I'm not sure if my command is correct. 2, 4, 1, 13. Okay, so I need to check the help of median because it did not produce the desired output. So help on median. Okay. Okay, so that's what I put was the dimension. All median returns the median value of A. If A is a vector, then median returns the median value of A. I think it's a median filter should be. Okay, median filter. Because here the word median did not mean filtering. Okay, there we go, median filter. So the command is midfilt1. And the size, okay, so let's try it here. Midfilt1, and the size is 3. Let's see. There you go. I think that's the answer we got. 2446. Can you confirm? It was 2446252. So when you use the word median, it will do the median process for the whole vector. And the number I put here by mistake was the dimension. So it was like looking at the depth. So it was the same values there. Now, when you do midfilt1, so it's a median filter for one-dimensional signal. That's that's what 1 means. And you put the input signal x and the size of the filter 3. And that will be the output. So it did zero padding automatically. You didn't have to do the zero padding. Now let's try the other example. MATLAB has opened. Okay. So the other example we had in the slides. So let's call it x2 equal 1, 2, 1. Okay. 493, 493. 3, 224, 224. Okay, so that's x2, 1493, 224. Now midfilt2. So the median filter for two-dimensional signal for my input x2. And you have to specify the filter, I think, by this. And let's see the output. If I'm correct, 0, 1, 0. Can you check? Same. All right. Now, probably to you for this example, it doesn't make a lot of sense because it's a small matrix. There is not much to see, but let's try to see it on an image. So let's see if the cameraman is there. IM equal IM read. That's the command to read an image. Let's see, cameraman is there. camera PNG, لا cameraman. Hopefully it's there, yeah. Okay, so IMShow is the command to display the image. IMShow of this image. So that's one of the common of images we use in image processing. So just an image of a guy using the cameraman. All right. Now let's add some noise to this image. We call that noise salt and pepper. Salt and pepper, because salt is bright, pepper is black. So you are adding outliers. And first of all, let's check the values of IM. You'll see here that it's an image, the size 256 by 256. If you want to find the maximum of this image, max of IM, and I had to convert it to a vector, because if we apply maximum to the image itself, it'll find the maximum of each column. It's a matrix, 256 by 256. So if you just apply maximum to IM itself, it will find the maximum of each column. It will return a vector, but I want to find the maximum of the whole image, 253, which is probably these values here. The minimum, similarly, I think you'll get 7, something like this. All right. Now let's add some noise. So let's add salt and pepper noise to image MATLAB. So there's the command IM noise. Okay, C. So let's call the new image IM2. IM noise the image. Now I'll pick the kind of noise as salt and pepper. And it will ask you about the density of that noise. So if you put 0, 1. Let's see how will that work. IMShow IM2. Let's see, there you go. See, like the image is not as clear as before. Like you notice here that this coat was all black. Now it has a lot of bright spots in there. Now let's try to apply a simple median filter of size 3 by 3. So the command IM, let's call the output filtered, equal mid filt 2 of the noisy image IM2, and the size of the filters is 3 by 3. Okay, it worked fine. Let's display the image. IMShow IM filtered. All right, and there you go. It's just a simple processing, simple filtering technique we used just to display the image. Okay, I'm zooming out and zooming in. But yeah, there are still some bright pixels there, like this one here. But when you compare to the noisy one, it still like looks really good compared to the immediate, like the initial one. So that's it. That's one of the applications of like the simple applications of media filters. You remove the outliers, like these dark pixels and bright pixels, the salt and pepper noise. And that's it for this lecture. It's a short one. And I think that will conclude the course. There is like another lecture at the end of the course. We'll talk about it later, but it's about some hardware implementations for DSP, but we'll not go into details of this hardware implementation, but we'll just talk about it, just for general knowledge. But in terms of our exams and the assessments, I think up to this material, that's it for the course. Starting next week, inshallah, we'll work on MATLAB, because there's the project. I gave you the project, right? لا, control I gave you. لا, I gave a project. The courses. Okay. Did you finish the courses, by the way? Okay. They have a project in the course or no? No. There's project. So we'll probably do some similar manner to that project. All right. So stop sharing. stop the recording. غير المكان من recording بقى.